Hello and welcome to the lecture 5 of the lecture series on complex number. Today we are going to learn the exponential function of complex variable. Let z is equal to x plus iy be a complex number. Then the exponential function of the complex number z is defined by e to the power z is equal to e to the power x plus iy. We can write, because z is equal to x plus iy, is equal to e to the power x cos y plus I sin y. Right, in case of complex number, we'll write, instead of e to the power z, we'll write exp z. So that means the exponential function of complex number z is exp z is equal to e to the power x cos y plus I sin y. Now, if the complex number z is equal to x plus iy is purely real, in this case y will be equal to 0. That means z is equal to x. In that case, the exponential function exp z will be e to the power x and cos 0 plus I sin 0. Cos 0, this is 0. So e to the power x into 1 plus 0, that means e to the power x. That means when the z is purely real, that means when y is 0, in that case the exponential function of the jx, that means exp z, will be equal to e to the power x. Now similarly, when the z is purely imaginary, that means z is equal to x plus iy. When it is purely imaginary, then in this case the real part x is equal to 0, we will get z is equal to iy only. So in that case, exp z will be e to the power 0 plus cos 0, not plus, it is into cos y plus I sin y. So it will be exp z will be equal to cos y plus I sin y. So when z is purely imaginary, in that case x is equal to 0, the real part will be 0. In that case, exponential of z exp z, that means exp iy, will be cos y plus I sin y. That can be also written as e to the power iy is equal to cos y plus I sin y. Now we know that this e to the power x is non-zero quantity. That means exponential function of for complex variable z is a non-zero complex number for any complex number z. Let us consider one complex number u plus iv, whose polar representation is r cos theta plus I sin theta. Since r is positive, we can write r as r is equal to e to the power log r, because so this comes from the formula of logarithm, because we can write any quantity in the form of logarithm like this: a is equal to e to the power log a. So we are using this properties, we can write r is equal to e to the power log r, since r is positive. So that means we can replace this r with e to the power log r. So that means u plus iv is equal to e to the power log r, and we know that this cos theta plus I sin theta can be written as e to the power I theta. That means exp I theta. So we can write exp I theta in place of cos theta plus I sin theta, because so this thing are same, e to the power log r exp I theta. This exp I theta can be written as e to the power I theta. So it will be e to the power log r plus I theta. So that means which can be written as exp log r plus I theta. So that means we are getting u plus iv is equal to exp log r plus I theta. What does it mean? This means when u plus iv is a given non-zero complex number, there exists a complex number z is equal to log r plus theta. This complex number log r plus theta, z is equal to log r plus theta, such that the exp log r plus I theta, that means exponent of log r plus I theta, which is equal to z, we have considered, which will be equal to u plus iv. What does this mean? This means the range of the exponential function of a complex number z is the entire complex plane excluding 0, because the exponential function of complex number is non-zero quantity. Properties of exponential function of complex variable. Number 1, exponential exp z1 into exp z2 is equal to exp z1 plus z2, where this z1 and z2 are the complex number. This is similar like in the case of real number. We know in the real number e to the power x1 into e to the power x2 can be written as e to the power x1 plus x2. Similarly, in case of the complex number z1 and z2, exp z1 into exp z2 can be written as exp z1 plus z2. Next is exp z1 by exp z2 is equal to exp z1 minus z2. This is also similar like in the case of real number. E to the power x1 by e to the power x2 is equal to e to the power x1 minus x2. We can write like this. So here also exp z1 divided by exp z2 is equal to exp z1 minus z2. Number 3, n be an integer, exponential function of z to the power n, that means exp z is equal to exp nz, like e to the power x whole to the power n is equal to e to the power nx, like in the case of real number. It is similar like in the case of real number. Next is, let n be a fraction, say p by q, then expz, exponent of z to the power n, has q distinct value, but exp nz is a unique, and it is the one of the value of exp z whole to the power n, because we know that this exp z to the power n can be written as exp z to the power p by q, because n is fraction, which can be written as qth root of exp z to the power p. So it will have q distinct value, qth root, since it is qth root, q distinct value, and exp nz is unique, and it is one of the value out of this q distinct value. This is one of the value of the exp z whole to the power n. Property 5, if n be an integer, then exp z plus 2n pi I is equal to exp z. So this is come from the property 1, that exp z plus exp 2n pi I can be written as exp z into exp 2n pi I, both are complex number, which is equal to exp z, and this implies this portion is 1. Exp 2n pi I is equal to 1, because this exp z and exp z will get cancelled, and then exp 2n pi I is equal to 1. So therefore by the property 1, exp 2n pi I is equal to 1, and this is obviously 1, because you can write exp 2n pi I can be written as e to the power 2n pi I, which is equal to cos 2n pi plus I sine 2n pi, and cos 2n pi is 1, and for any value of n, and I Sine 2n pi is 0, so which is equal to 1. So this result is obvious. Exp 2n pi I is equal to 1. This shows that the expz, that means exponential function of complex number z, is a periodic function of z with the period 2n pi I, because see, expz plus 2n pi I is equal to expz, so the period of this periodic function is 2n pi I. So this is the period of this periodic function. Let exponential of function of z be w, where w is a non-zero complex number. Then we can write the exponential of z plus 2n pi I is equal to w because of this property. Thus, for a non-zero complex number w, there exists infinitely many complex number z, because when you run the value of this n is an integer, so you will get infinitely many complex number, such that the exponential function of z, that means exp of z, will be equal to w. Let's do one question. Question is, find all complex number z such that exp z is equal to 4i. Now we will consider this complex number z equal to x plus iy. Then exp z can be written as e to the power x cos y plus I sin iy, so which is equal to 4i by the equation exp z is equal to 4i. So we can equate the real part and imaginary part. Real part is e to the power x cos y. Here the real part is 0. E to the power x cos y is equal to 0. And imaginary part is e to the power x sin y is equal to 4. Here the imaginary part is 4. Now from the e to the power x cos y equal to 0, e to the power x cannot be 0, so cos y is 0. So that means here cos y is 0. Cos y 0 means cos y is equal to 0. That means cos y is equal to cos pi by 2. This can be written as cos y is equal to cos 2k pi plus pi by 2, because for any where k is an integer, if you run the value k as an integer, so this will give cos 2k pi plus pi by 2 will give you cos pi. So from here we can say that the y is equal to 2k pi plus pi by 2. So y is equal to 2k pi plus pi by 2, where k is an integer. Now y is equal to 2k pi plus pi by 2. So sin y 2k pi plus pi by 2 is sin pi by 2, which is equal to 1. So we'll get e to the power x is equal to 4. E to the power x is equal to 4. So if e to the power x is equal to 4, then you can take the log on both sides. X will be log 4. So therefore our complex number z will be x is log 4, I is I, and y is 2k pi plus pi by 2. So we can write z is equal to log 4 plus 4k plus 1 pi I by 2. Thank you.